right? Hermitian matrix, and x is greater than or equal 0. Greater than or equal to 0. Okay, this means that x is non-negative. Definitely. Okay, we have two conditions. If x is Hermitian, and the second one is x is non-negative, definite. Then the eigenvalue decomposition and the single value decomposition are the same. And the single value lambda I, the eigenvalue lambda I equal to the single value sigma I for OI. And we also have U equal to V. U equal to V. And this vector is unitary. That's in the first property. So it means that in the case of Hermitian and non-negative definite matrix, then the eigenvalue become the single value decomposition. Now, given the singular value decomposition, in which x equal to u sigma vh. Suppose we have this singular value decomposition, and this one is a matrix m by n. Here we suppose that m greater than or equal to n. And we have sigma. Sigma is the diagonal matrix. Okay, maybe I write like this. Diagonal matrix whose diagonal entries are sigma 1, so on, sigma n. Diagonal matrix means that the entries on the diagonal are sigma 1, sigma 2, and so on, sigma n. All other entries are 0. Then the eigenvalue decomposition of the matrix x times xh, right? X times xh is the following. Given by the following. Now you have u. Now we replace x by u sigma vh. Yes, multiply with u sigma vh h. And actually that's in here, yeah. And it's equal to, we have u sigma vh. Now Hermitian transpose of this product equal to v Hermitian transpose sigma Hermitian, and u Hermitian, right? Because we know that the Hermitian transpose product equal to the product of two Hermitian transpose when we swap the order. And then you see this one. What is it here? This one turned out to be the following. This is u sigma v Hermitian. Remember Hermitian up back v, and then sigma Hermitian and u Hermitian. But then you know that because v is unitary matrix, and this one become I. Identity matrix. Therefore, this one become u. U sigma multiplying with sigma Hermitian and multiply with u Hermitian transpose. Yeah, and now we see the following, everyone. We see the following. we have sigma. What is it here? You can imagine sigma in the following. Sigma is, you can imagine it like the following. Now this is sigma 1, sigma 2, so on, sigma n. And here we suppose m greater than or equal to n. Therefore, we may go down here, yeah, and maybe here. But then everything here is 0, and everything here is 0. Okay, imagine like this. Let me see. Hang on. Let me check. Yeah, this is m row and n column. This is m row and column here. M row and column. And let me see. And then if sigma like this, then we can find out sigma Hermitian. Sigma Hermitian is what? So you got Hermitian of this one, that it becomes an n by n, yes? And then you have sigma 1. Okay, sigma 1, sigma 2. You can imagine so on. This is sigma n. And you can imagine this is 0. All 0 here, everyone. Yeah. It's like this. That is sigma h. And then we can find out sigma multiply with sigma h. Yeah. Sigma multiply this matrix multiply with this matrix. And what is it here, everyone? So imagine like maybe I should write explicitly a little bit more. Sigma 1, 0, and so on. You can imagine you have 0 here, then you have 0 here, you have sigma 2, and all 0 here, and then you have 0. Okay. And then this go on, and then you can imagine to some point here. This is sigma n. Sigma n. Go this way. And then you have 0 here, 0 here, so on. But then you keep going. 0 here, 0 here, or 0 here. You can understand that way. This is sigma, everyone. This is sigma. And sigma h. Let me write down here. Sigma h. This is sigma 1. 0, so on, 0, 0, sigma 2, so on, 0. And then you can imagine like this go to this point, sigma n, then 0 here. And here's all 0 down here, 0 here, like this. And this one is n by n, multiply with n by n. Yeah. And this one become, okay, I may write here. Now you see, this row with this column, then we have sigma 1 squared. Hang on. I'm not a mistake, everyone. I need to try the conjugate here, sorry. I missed this one, the conjugate. But then you see, sigma 1 multiplied with the conjugate of sigma 1, it becomes the modulus square. Modulus square. This one. Is it modulus square? Hang on. I think we get wrong. Okay, I guess. Sorry, everyone. Sorry. Because in the singular decomposition, we have sigma 1 is sigma. This sigma are real number. Everyone, sorry. I missed one point. The one we only consider real number only. Yeah, because it's a singular is real.
Đích thử là mình đích
The number are real. The number are real. Yeah. Because by definition, in the single value decomposition, then the sigma is that matrix in which all the singular value are real number. Are real number. And greater than equal to 0. Actually, we have one more condition, greater than equal to 0. So if we do the calculation, this one, we don't have to worry about the modulus because it's a real number, sigma 1. If we multiply this row, this column, then you have 0, and so on. This is all 0. And this is n by n, the result is n by n here. And the second one is 0 here. This is sigma 2 square, and you can imagine all 0. And then this row, this row, this column, then we would have 0 here. Go on, and this one is sigma n square. You can imagine like this, and all 0 here. And then you have basically here all are 0. This is 0, 0, and all are 0. I mean from here is 0 already. And then you have this matrix. And this matrix then people can draw it in the diagonal. Sigma 1 square, sigma 2 square, so on. Sigma n square. And some other entries are all 0. All 0. And this is on the side n by n. N by n. Okay, so that's the eigenvalue. That's the eigenvalue decomposition. Like this. Yeah. It's not good. I didn't have a good arrangement with my so I have to draw it down. So we have here, everyone. So we have here. So basically, maybe I write here. Okay. Therefore, we have the following, everyone. Therefore, we have the following. We have x times x Hermitian. This becomes U. This becomes matrix U, the unitary matrix U. Multiply with this matrix, diagonal. Sigma 1 square, sigma 2 square, and so on. Sigma n square, 0, and so on. 0 here. And multiply with U Hermitian transform. That's the way. We have the eigenvalue. If x has the singular value decomposition like this, then the eigenvalue of this one, x transpose, is given by the one over there. Okay, just write like this first, and then we will have some comment later. Now, the eigenvalue, the other one is the eigenvalue decomposition of x Hermitian transpose times x. Okay, is the following, everyone. We write x Hermitian transpose times x. Now, x Hermitian transpose is, we have U sigma v Hermitian transpose or Hermitian transpose multiply with U sigma U Hermitian transpose. And then remember, Hermitian transpose or product equal to the product of Hermitian transpose, but with the opposite direction. So we have V Hermitian of Hermitian, sigma Hermitian, U Hermitian, then you have U sigma. No, I'm wrong. I'm not aware. This is V, sorry, V Hermitian. And then you see this one basically because U is because U is unitary, then this one becomes the identity, everyone. See that? So this one become, now V Hermitian transpose, it become V. And then we have sigma H times sigma and times VH. Now, sigma H, now look at it. What is it here? Now we can see this one. Okay, we do this calculation. Now we'll do this calculation. We consider the sigma Hermitian. Now here, sigma Hermitian times sigma. And sigma Hermitian, we look over there. You can imagine this is the sigma 1, 0, so on to 0. This is 0, sigma 2, so on to 0. And then go down 0, 0. Let's go down to some point here. This is sigma n, and then all 0 here. You can imagine like this. This one, you imagine 0 here, everyone. Yeah. That's the n by n. The n by n. Now, times sigma. Now, times sigma. This is sigma 1, 0, and so on, 0. This is 0, sigma 2, so on, 0, and so on. We have some number here, we have 0 here. Let's go to sigma n. And then we still have 0, 0, and so on, 0 here. This is like this. And this is m by n. M by n. And then we do the calculation. This one equal to what? This will be an n by n matrix. Now, this one with this one, sigma 1 squared. This one with this one, 0. And so on. This one with this one, 0. Now, this one with this one, 0. This one with this one, sigma 2 squared. And then this one with the next one will be 0 and so on. Finally, you all have 0 here. Then go on. And this one with this one, we have 0. This one with the second one, also 0. And finally, this one with this one, we have sigma n squared. Okay, match it like this. That's what. So basically, people can write the following one. Diagonal of sigma 1, sigma 2 squared, and so on. Sigma n squared. Okay, and therefore we have the following. And therefore, we have the x Hermitian times x is become v. It's become v times the diagonal. Sigma 1 squared, sigma 2 squared, so on, sigma n squared, and multiply with v Hermitian transpose. V Hermitian transpose. Yeah, you compare the two. X Hermitian is u diagonal of, that's one, right? And u h, and then you have that one.
The matrix should be n by n.
N by N, sorry. N by N. Okay, this one is very important, everyone. This one is very important. Now, we try to summarize. Okay, we try to summarize the calculation we have just shown here. Then we have the following. Now, summarize the second property. Now, we have the singular value decomposition. The x equal to u sigma vh, and this one belongs to the c m cross n, for example like this. Then we have the following. Then the x times x Hermitian the x times x Hermitian is A equal to U. The diagonal of sigma 1 square, sorry, sigma 2 square, blah blah, sigma n square, 0 and so on. 0 and multiply with U Hermitian. Okay, that's the first one. Now the second one, x Hermitian times x Hermitian times x, is become V diagonal of sigma 1 square, sigma 2 square, and so on, sigma n square, like this, and V Hermitian. Okay. Just give me 1 second, everyone. You have. So here you see, then you see this is the. So here you see sigma 1 square. Yeah. From here we can also learn something. From here we can also learn something. Let me. Should I write off? This is a relationship only. So sigma 1, remember sigma 1, sigma 2, so on, sigma n, they are singular values of the matrix X. But if you look at here, then sigma 1 square, sigma 2 square, sigma n square, they are eigenvalue of X multiplied with X Hermitian transpose. Yeah, and they also are eigenvalue of X Hermitian transpose times X. That's very special, because that can help us to find out the singular value of a matrix X. Like for example, eigenvalues are easy, right? Eigenvalues are easy. But what is singular value of a matrix? For example, if I give you a matrix X and ask you to find out eigenvalue, we know how to do it already. We build up the characteristic polynomial. Remember the p x lambda, and then let the p x lambda equal to 0. We can find out eigenvalue. Now, okay, that's it for eigenvalue decomposition. For singular value decomposition, we have another number, sigma 1, sigma 2, so on, sigma n. They are called singular value of a matrix. What are they? So by looking at the two identities, then we realize that if sigma 1, sigma 2, sigma n are singular value of the matrix X, then sigma 1 square, sigma 2 square, sigma n square, they are eigenvalue. Because you see, this is the form of eigenvalue. Eigenvalue of X multiplied with X Hermitian transpose, or X Hermitian transpose multiplied with X. That's what we learned from there. So it means that if you are given a matrix X, and if the question asks you to find out singular value, right? Remember, singular value, they are greater than or equal to 0. Therefore, if you can find out sigma square, then you can find out sigma, right? Because you only took the greater than or equal to 0 number. So now if you are given a matrix X, then in order to find out singular value of X, then you first find out X multiplied with X Hermitian transpose. And then you find out all eigenvalue of the X multiplied with X Hermitian transpose, or this one also, they are the same. You can either go with this one or this one. And once you have the eigenvalues of this matrix, then you just need to take the square root, and you have the singular value of the matrix X. That's the idea. Okay, next we go to sum property. Okay, so far we have considered the differences and the relationship between single eigenvalue decomposition and singular value decomposition. Now, next we go to sum property. Some properties of singular value decomposition. Some property of. Now, P1, property 1, all singular values of a unitary matrix, all singular value of a unitary matrix X are 1. Okay, that's the first property. Maybe we consider a short proof here. Now, for example, we have X to be, now X, okay, X you can write in the following form. X equal to X multiplied with the identity multiplied with the identity. Is it okay to write like this, everyone? The matrix X equal to the matrix X multiplied with the identity and multiplied with the identity. Remember, identity multiplied with any matrix give you back that matrix, right? So X multiplied identity is X, X multiplied identity is X, therefore I can write like this. It's okay, right? And then you see, this is unitary. This is unitary because the assumption here is X is a unitary matrix, so this is unitary. The matrix I also unitary. Do you remember what is a unitary matrix? Unitary matrix, it means that all the column vectors, they are orthogonal. Yeah? And I, of course, is satisfied this condition already, so we have no worry about I, right? Remember, we have the VI, the column VI, dot product with VJ equals to delta IJ, the collector delta, the one that we have on last week, I think. Last week, yeah. Yeah. So we have that one. And then you see, this one, why is it here? Imagine this is n by n. You can imagine this is n by n. This is n by n. This one must be what? This identity must be of which side? Actually, this is I by n by n. This is n by n. Okay? And then you see, it means that you can write down x into the form of x m by n, right? This is m by n. And multiply with this matrix everyone. 1, 1, 1. That is I n, right? You can imagine this is the matrix U, everyone. This is the matrix V. You can understand V transpose, Hermitian transpose, yes? And this one basically is sigma. Okay? And if it's in like this, here, you see, they are singular value. They are singular value of the matrix X, right? And clearly they are 1, 1, 1, 1, and so on. So that's what the property tells us. Is this still okay? This means that if you can write X in the form of U sigma VH, in which sigma is a diagonal matrix, yes, a diagonal matrix, then the entry on the diagonal are singular values of the matrix. And in this case, you see all number 1. It's all number 1. That's the property 1. Now let's go to the second property. 42. 42. All singular value. All singular values of diagonal. All singular value of a diagonal matrix. Of diagonal matrix X equal to diagonal x1 and so on xk belong to C m by n. Let me see. With k here, with number k equal to the minimum value of m and n are the absolute value. The absolute value x I. Okay, yeah, x I. It means that if you have a diagonal matrix, everyone, for example, here you can imagine like, okay, the proof. You can imagine like your x is the following. Your x is the following. This is a diagonal matrix. You can imagine like this is the following. This is x1. You have x1. You have 0 here. Then you have 0 here. You have 0 here. x2 and so on. 0 here. And then you can imagine this go to x k here. Actually, this k equal to min m and n. I suppose m greater than, in this case, I suppose n greater than n. This is 0 here, sorry. 0, 0, and so on here. This go down here, 0, 0, 0 here. Yeah, this is m by n. No, this is m by n. Okay, if x like this, then I can write down x in the following form, everyone. X, I can write down is in the following form. I have the following vectors. I have the following vector, vector u, and this is an m by n vector here. And I have the following. This is x1 divided by the modulus of x1. And here I have x2 divided by the modulus of x2. Okay, I need more space. So this is 0 here, so on 0, this is 0, so on 0, and so on 0, 0, and so on. Here I have x. So in this case, everyone, in this case, k equal m, right? K equal n, sorry. K equal n, like this, right? So I have to check carefully this one. Maybe I make mistake here. Okay, here in this case, I suppose n greater than n. Right? Then I have a form like this. And then I have I have to get that carefully. With x, I want x to be like this. M by n, m greater than, so I have that's 1. And then I can write in which form? Well, okay. Yeah, I think I should be very careful with this one. So this is 0 here, 0 here, sorry, I think I need one more column here, maybe 0 here, and then 0 here, 0 here, and this one I have x n divided by the modulus of fn, like this. This is 0 here, this is 0 here, and now this go 0, 0, 0, and then this 0. You can imagine all 0 here. You can imagine all 0 here. And this is the m by n. The m by n. This is m by n. And then I multiply with x. I multiply with x. I multiply with x. Let's rewrite it. This is x1, 0, so on, 0. 0, x2, so on, 0. Go to 0, 0, so on, xn. And then 0, 0, so on, 0. See, like this is m by n. And then I multiply with the last matrix. I have to be very careful. The identity matrix, I think. No. No. M by n. So on this one, I check the modulus here. I check the modulus here. And then here I multiply with 1, 0, so on, 0, 0, 1, so on, 0, and so on, 0, 0, 1. Like this, I have this matrix, and this is n by n. I take one like this. Right? For example, if you want, x like this, I can write x like this. For example, you add this one with this one, then you got x1, right? And then you have all 0, and you can see that you multiply this one and this one, then you got x, basically. But then this one is just identity matrix, so this will be everything. And you can understand that this is U. This is U. This is the unitary matrix U. This is the sigma. And this is V. You can check easily. For example, if you take this column, you can imagine you have this column, you multiply with this column, then you got 0. But if you take this column, multiply with this cell, you got number 1. You will see that you will got number 1. Yeah. Therefore, yes, this is a unitary matrix. This is sigma because you see this is a diagonal matrix and all the entry on the diagonal are greater than or equal to 0 because they are modulus. And then this is the identity matrix clearly. You see this is the identity matrix and an identity matrix, a unitary matrix, so you can have that form. Yeah. So if X is a diagonal matrix, then this is the singular. You see? They are the singular. And they are the singular of the matrix, the diagonal matrix, and the the modulus. Okay, this is the second property. Now we go to property 3. We go to P3. If X belongs to C M by n, I mean there n, X is invertible. X is invertible. It means the determinant of X is non-zero. Okay. Then the singular value, the singular values of X. Okay, maybe I think it's better if I do the following. Suppose that X has singular value. Suppose that X has singular value. sigma 1, so on, sigma n. Yeah, suppose that x has singular value sigma 1, suppose sigma n. Then the singular value, then the singular values of x inverse, the singular value of x inverse are the following, are 1 over sigma 1, so on, 1 over sigma n. I mean, just we check the inverse, right?
Mày
Number.
quen mà gì? Cái xe kia, cái xe xuất á. À, bao nhiêu tiền?
And the left, and right, the left and right singular vectors, the left and right singular vectors, left and right singular vectors of x inverse, are the right left and the right, or the left singular vectors.
cái quét test nhìn ngán.
Of x.
Cái đó bữa có thể cho làm rồi.
Okay, the proof now. We go with the proof. We go with the proof, everyone.
Cái đó cái này là phần entropy mới không?
Okay, we have the singular value decomposition of x. Suppose that this is the following: U sigma v transpose, Hermitian transpose. Then, if we consider x inverse, it becomes U sigma v Hermitian transpose inverse. We know that if the inverse of the product equal to the product of inverses, but then we swap the order. Therefore, we have this one become v Hermitian inverse times sigma inverse times U inverse. Okay, because U is unitary matrix, right? U is unitary matrix, then V Hermitian inverse, thus it become V sigma inverse and U inverse. You have U equal to the Hermitian as well. Because unitary matrix, it means that the inverse equal to the Hermitian, right? Yeah, the inverse equal to the Hermitian. Therefore, we have this one. So basically, you see here. And then you see if and sigma, remember, okay, imagine like, now how can I write? What is sigma here? You have to understand sigma is the following everyone. Sigma here is the diagonal of sigma 1, so on, sigma n, right? Then this one turn out to be diagonal of sigma 1 inverse, so on, sigma n. You can check quite easily. Here, what I mean here is the following. Maybe I explain here a little bit more. This is the following. For example, you have sigma here. Sigma equal to sigma 1, sigma 2, 0, 0, 0, 0, 0, 0, sigma m. And then you can easily find out sigma inverse is the following. Inverse 0, so on, 0, 0, sigma 2 inverse 0, so on, 0, 0, sigma m inverse. Very easy. And then you see, if you see clearly, right, from here, then you can conclude that the singular values of x inverse equal to 1 over sigma 1, 1 over sigma 2, and so on, 1 over sigma n. Okay, and the last property, P4. Last property. The two norm. the two norms of any matrix X, the two norm of any matrix X is largest. Any two norms of the two norm of any matrix X is its largest singular value. Sigma max. Sigma max. And can we prove it? Now we go to the two norm. Then we have the proof. The proof here. So the two norm of a matrix X equal to the maximum of the two norm of X multiplied with a matrix A, a vector A. Yeah. And with the condition here is that the two norm of vector A equal to 2. Okay, if you forget about the norm of a matrix, then please we go back to the, I think the first lectures. Let's see like this. Okay, and because of that, then this one becomes the maximum. The maximum of what now? The two norm XA. I can reply XA by U sigma V Hermitian transpose. U sigma V Hermitian transpose multiply with vector A and the L2 norm. Okay, and we have the following. This is for A, this is L2 norm, the L2 norm A equal to 1. Yes, and then since U and V are unitary, then they do not change. They do not change. They do not change the L norm, the two norm, yeah, the two norm. They do not change the two norm of a vectors. Two norm of the vectors, and therefore we have the following. Therefore the norm, you can imagine like the two norm of X is become the max now. This becomes the max. I can draw like this, and then I have now look at here. Then you see this norm. You can imagine that because V does not change the L2 norm of A. Therefore, I can draw it into the following form. It becomes the L2 norm of U sigma B. Because if the L2 norm of A equal 1, then the L2 norm of B HA equal 1, and then I replace this one by B. I see L2, and with the condition here, the L2 norm of B equal 1. And yeah, and because we know that U is unitary, then the L2 norm of this one equal to, and this one be equal to the max of the L2 norm of sigma B. L2 norm with the B equal to the L2 norm B equal to 1, and I can have that one. What else? Yeah, I stop there, but I need something more. Sigma B. Yeah, then we have to understand what is here. The L2B, L2 norm. How can it become the sigma max? I see. Okay, I can explain it a little bit more here. Now, I can do the following. To clarify clearly. We have sigma b. Then suppose that we have the following sigma. Yeah. Suppose us. Now, suppose that we have sigma is the following. Sigma is the following one. This sigma 1, sigma 2, 0, so on, 0, 0, 0. 0, 0. This one goes to sigma n and more. 0, 0, and so on, 0 here. This is n by n. N by n. And suppose that, and here, sigma 1 equal to the maximum of sigma I go from 1 to n. Suppose like this. Yeah. Then we choose. Now we choose b. Vector b equal to the following one. Vector b equal to 1, 0, and so on, 0. Transpose. And then we have sigma b. Sigma multiplied with vector b. We multiply this one with this one, then this one will become sigma 1, 0, and so on, 0 here. Transpose like this. And therefore, in this case, the L2 norm of sigma b, L2 norm of sigma b equal to sigma 1. Because this is, this is a square root of sigma 1 square plus 0 square plus so on and plus 0 square. And this equal to sigma 1. And that's the sigma max, the biggest. Because here we suppose sigma 1 is the biggest. Singular value. Yeah. Okay, and remember here, we have the norm, the L2 norm of b equal to 1 here. Therefore, according to this one, then we have the following. Because the L2 norm is the max, so it means it must be greater than or equal to for all this one, for all b simplify this one. Therefore, we have the norm of x, the L2 must be greater than or equal to the L2 norm of this one, of this b, right? Must be greater than or equal to sigma 1, sigma max. What is the first one? Now, for all b, such that the L2 norm of b equal to 1, we have the following. We have the L2 norm of sigma b. The L2 norm of sigma b is equal to what? Let me see. I do the calculation. I take sigma, I take sigma. I write it again here. I have sigma 1, 0, so on, 0, 0. Sigma 2 or 0. Now we go to 0, 0. And then we go to sigma n. And here I go to 0, 0. And I go to 0 here. This is n by n. Yeah, this is n by n. I multiply with b. B what? B is the n by 1. So this is b1, so on, bn. This is n by 1. Like this. Hang on. No, I think I should have this one first, yeah. And then I have the vectors. What is it here? This one with this one. I have sigma 1, B1. This one with this one. I have sigma 2, B2. And so on. This one with this one. I have sigma n, Bn. And all here is 0. 0 here. You can mention 0 here. And this a m by 1. M by 1. It's very complicated. Yeah. Maybe I can write a bit more here. And therefore I have the norm, the L2 norm. What sigma b? The L2 norm equal what? This equal to now sigma 1 b1. I remember they are. So you have to check the modulus, everyone. Plus so on plus sigma n bn, the modulus square all to the power of half. Like this. Yeah. Okay, now we keep going with that one. So the L2 norm of this one equal to the square root. Basically, this is the square root of sigma 1 b1 square plus blah 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 plus sigma n bn modulus square. Okay, but then you see this one you can must it become the two modulus. Remember the modulus of a product equal to the product of two modulus. Therefore, this one is this modulus multiplied. Then I can split into the product of two modulus like it. And now this one is smaller than or equal to the max, the sigma max. Go slowly. Square root, keep the square root. And then you see, remember sigma 1, sigma 2, blah blah, sigma n, they are real number. They are real number and they are greater than or equal to 0. That's the definition of singular value. Therefore, this one equal exactly, I can drop the first one, sigma 1 times modulus of b1 squared. So on, plus sigma n times modulus of bn squared. I can drop like this. And then this one is smaller than or equal to the square root of sigma max b1 squared plus so on sigma n bn sigma max bn squared like this. Yeah, because sigma 1 smaller than or equal to sigma max, sigma 2 is smaller than or equal to sigma max, and sigma n is smaller than or equal to sigma max. Sigma max is the biggest one among sigma 1 blah blah sigma n. Then you can, oh no, I missed something, right? Square here. Yeah, square here. Square here. So I put sigma max square outside at a common factor and put it outside the square root, and this one become sigma max multiplied square root of b1 squared plus so on bn squared. And this one turned out to be the norm of b2. And this equal to sigma max. Okay, so you see here. No. Okay, we have proved this one. This is number 1. Now we have proved, so from here, this means that we have proved the following. We have shown that we have proved that for every vector B such that the L2 norm of vector B equal to 1, there holds the sigma B2 norm is smaller than or equal to sigma max. Right? This is true for all B2 equal to 1. Therefore, we can have the maximum of the norm B L2, in which for every B such that the L2 of B equal to 1, this maximum is smaller than sigma max. Because it's true for all B. Then if you take the maximum, then the maximum is still smaller than sigma max. And it means that according to the definition, it means that the X norm, the L2 norm of X is smaller than sigma max. This is true from 1 and 2. We have proved that we have the L2 norm of X equal to the sigma max, and that's what we have to prove. The biggest singular value. It's not easy, right? Quite tricky. The technique is very simple. Like for example, I want to prove. For example, I'm saying that the maximum, we take the maximum of age of all students in the class. I want to prove that the maximum age of students in this class is 30 years old. Okay? I want to prove that this. Then I do the following. First I consider the age of all of you in the class, and then I check, okay, all of you, the age is less than or equal to 30, you less than or equal to 30, all of you less than or equal to 30. Therefore, the maximum age of student in this class is smaller than or equal to 30. But this is I only have smaller than or equal to. I want to have equal, then I pick up one. If I can choose that one of you who was born in 1994, this means that your age, that's the age of that student is 30. This means that the maximum, okay, must be greater than or equal to 30. Right? We have shown that the maximum age of student in the class is smaller than or equal to 30, and then I have shown that there is one student in the class whose age is greater than or equal to 30. Therefore, I can conclude that the maximum age of the student in the class is equal to exactly to 30. Of course, for the case of age of the student, that is easy. You don't have to do like this. That's the demonstration of the idea. Yeah, in the slide prepared by Professor Yang Ping, that is just one sentence. The proof is just one sentence, but a lot of things behind. Just one sentence. But if we're talking about the proof, understand what the proof is, then this doesn't help you. You can make this line shorter by better way of writing it. It's not that short like in the slide. Okay, that is some property of singular value problem. And we next go to the next section, condition number. We next go to condition number. Condition number. Now the condition number. The condition number of any invertible matrix X. Invertible matrix X is defined as the following: the condition number, the kappa of X, kappa of X is defined to be the norm of X multiplied with the norm of X inverse, where, okay, maybe I write down here, where this one may be any matrix form. Maybe any matrix form. Matrix norm. Maybe any matrix norm. It could be L2 norm. It could be infinity norm. It doesn't matter. Yeah. Maybe any matrix norm. Typically, the L2 norm is used. Normally we use the L2 norm. Then the condition number. Okay, so the condition number depends on the way we define the norm. But if we define the norm to be the L2 norm, then the condition number is the following. It become kappa X become the L2 norm. The L2 norm X multiply the L2 norm of X inverse. Yes. And it turned out to be the sigma max divided by sigma min. And this one normally greater than or equal to 1. Yeah. Where sigma max and sigma min, sigma max and sigma min are the largest, and the smallest singular value of X. Yeah, X. Okay, and I need to change the pen. Now, if the matrix X is if X is Hermitian matrix, if X is Hermitian and if X is Hermitian and X is greater than, non-negative definite, then the condition number of X equal turn out to be the biggest eigenvalue divided by the smallest eigenvalue. Okay, where lambda max and lambda min are the biggest, are the largest, and the smallest. The largest and the smallest eigenvalue largest and the smallest eigenvalues of the matrix X. Of the matrix X. Okay, that's the condition number. Okay, and why do people need the condition number? Okay, we have the following remark. We have the following remark. The condition number. The condition number kappa x of matrix X is used to measure how well X inverse can be calculated numerically. Okay, again we have some special case. We have some special case. If kappa x equal to infinity, then it means that x is singular. What does it mean by singular? It means that x equal to 0. That x equal to 0. Okay, and here and the lambda mean and the sigma mean, the smallest singular value equal to 0. And if kappa of x is very big, I mean it's very much larger than number 1. Right now this means that kappa x is greater than 1 a lot. Yeah. In mathematics, when people write out it means that it's greater than 1 a lot. That it means that the biggest singular value is much greater than, much larger than sigma mean. Okay, then in this case, x inverse exists. However, a small error in x results in big error, large error in x inverse. Okay, that is something about condition number. Condition number play a very important role when you do the calculation numerically. Okay, now we still have the rank, the subject is Okay, let's have a break anyway. 823, 831, 832, 833. And then you need to multiply with some matrix here. And such that you have the following everyone. You swap column 1 with column 3. This is A13, A23, A33. This is A12, A22, A32. This is A11, A12, A13. Yeah, so you see, can you see that? We swap, right? This column, right? This one, and this one. Can you see that? Now, because that is something about the column, then I guess that I have to multiply with something here. I have to multiply with something here. Now imagine, I multiply with this one with a column here. But then I get, what is it? A13 only.
No, tự nhiên I have some question.
Yes.
So we have just the statement if it replace the third column by the first column of A. So it is not a swap.
I replace.
Yeah, replace not swap. So basically we copy the first column to the third column.
Replace the first column. Replace. It's not swap. Yeah, you're right. Now, replace column 1 by column 3, right? Replace column 3 by column 1. This means that here, okay, here this one is still A11, A21, and this is A31. The same here, right? Okay, now, it seems like this one multiply this one, you should have this one. So maybe this is something like 1, for example. Now, this one you multiply this one, you got A11, right? This one, you got A21. This one you got A31. Okay, right? Now, the second one, now you see, you multiply this one with this one, you got the one in the middle, right? So maybe the one in the middle, then you have 0 here, you have 1 here, and you have 0 here. Now, this one multiply this one, you got A12. This one with this one, you got A22, correct? This one with this one, you got A32. Okay. Is it okay? Now, you multiply this one with this one, but you don't have A13, but you have A11. Right? So maybe this is number 1 here, and number 0 here, and number 0 here. Now, this one, this row, you multiply with this one, you got A21. No, I'm wrong here, right?
Yeah.
This is A21, A33, sorry. Yeah? And this row with this column, you got A31. 31. Is it okay? Now we understand the rule. This is replace the first row by the third row by the first row. Third column by the first column. Now imagine if I do the following. Replace row 2 by row 3. How about that? Now we know that because this is a row, right? So maybe I multiply on the right, so I put this is A11, A12, A13, A21, A22, A23, A31, A32, A33. Yeah? And now I want row 2 by row 3, so I keep the first row, A11, A12, A13. Now, I want to have A31, A32, A33. This is A31, A32, A33. And then because this is row, so I guess I multiply some matrix here. Okay? Now, if we change something with row and we multiply to the left, if you will change something with the column, you multiply a matrix on the right. Keep in mind. Yeah. Now, what is it here? Now, I consider row, right? Now, this row multiply with this one, I have A11. This row multiply with this column, I have A12. And this row with this column, I have A13. So you see, maybe this is 1, oh. Can you see that? Yeah. Now, for this one, now, this one, with this one, I have A13. So maybe number 1 should be here, right?
Yes.
Yeah. And then this one is 0, 0. Now check. This one with this one, I have A31. This one with this one, I have A32. This row with this one, I have A33. Okay? Now the last one, I keep it the same. Multiply this one, I should have this one. Right? So it's A, what is it, everyone? O1. Is it? No.
First one. One on the left.
One moment. If I multiply this one with this one, I have A31. This one with this one, I want A32. And this one with this one, I have A32. It seems to be okay, right?
Yeah.
Okay. Next, we go to C. The C. Have first column of A. Okay, this is about column. So I get that I will multiply with something on the right. So we got A11, A12, A13, A21, A22, A23. A31, A32, A33. And I multiply some matrix here because this is about a column. And then half third column. This means that I divide column 3 by 1/2. And I divide column 3 by a half column 3. So I keep the first 2 columns. Hello? Now, this one I want to have 1/2. 1/2. 1/2. Okay? Now you see, I multiply this one with this column. I should have A11. This one, and then I have A11. So this one should be 100. Now check. This one with this one, then I have A21. This one with this one, I have A31, correct? Now is the second one. The same, right? This one with this one, I should have A12. So maybe the number 1 must be here. Yeah, and then you check this one A22, this one A32. No, I'm wrong. 32. Yeah. Now, I multiply this one with this one. I should have a half of A13. Hang on, something wrong, right? No. This one with this one, I have a half of A13. So it's a half here. And this is 0 here, this is 0 here. And then you see this one with this one, I have a half A32. This one, I have a half A33. Yes? Last one. This is half first column A. And then we should have the same one with the, if you multiply one row with some number. Yeah. Maybe we can go to one example. Another example. Another example. For example, you have the matrix here. A11, A12, A13, A21, A22, A23, A31, A32, A33. And then imagine like I want to have the row. Imagine like I want to make this, I keep the first row. A11, A12, A13, and now a third, A22, a third, A23. Now this one I made it slightly different. I want to have 4 A31, 4 A32, and 4 A33. Okay, two of them. Is it possible to do it? Let me remember. Is it possible? Sometimes it's not easy to go that way. Maybe we should go step by step, for example. Just to be careful. No. Normally we should do it slowly, everyone. Two at the same time, sometimes it's impossible to find. It's very hard to find. So I'm going to multiply this matrix. I'm going to multiply this matrix, and then you see this one. I keep the same here, so I have 1, 0, right? This one, yeah, okay. This one I have O, half, O, and this is O, 1. You can see like that. You can check. Yeah.
1/3. The 1/3.
Oh, 1/3. 1/3. So okay. Yeah. So anything happen with row, multiply a matrix on the left, right? And it happened with column, multiply a matrix on the right. Now let's go with D. Interchange row 1, we swap it with row 3. Okay, because this is about rows. So you imagine the matrix here. A11, A12, A13, A21, A22, A23, A31, A32, A33. Now you want to have the matrix in which you swap the two rows. So this is A31, A32, A33, A21, A22, A23, A11, A12, A13. Can you see that? You can see this one and this one, right? And now this one become here and this one become here. And then because this is about row, then I multiply with a matrix here. Now, imagine you have the first row. The first row here multiply with this one, but you pick up the last one, right? You pick up the last one. How can we pick up the last one? Then this one should be what? O, 1. Is it? Yes. Now, you multiply this one with this one. Then A31, this one, A32, this one, A33. Okay, it's okay. Now, how about this one? You multiply and then you see that the second row stay the same.
0, 1, 0.
O, What is
One.
it here?
1.
Because it stays the same here. Now, this one, you multiply this one, but then you multiply with this one, you pick up this one, not this one. So this is
1.
okay. Are you understand the rule now and how to find it, right? And interchange columns are similar. You multiply with a matrix on the right. Okay, now E. Subtracts 3 times. Subtract 3 times. Second row. 3 times second row. From first and the third row. Okay. Okay, it's about row, right? It's about row. So I suppose I multiply with some matrix on the left. So A here, A11, A12, A13, A21, A22, A23, A31, A32, A33. Now I want to have what is it here? What is it here? Subtract 3 times the second row from the first and 3 times from the second row from the third row. So this one should be what? Here should be what? A11 minus 2 times A21. And it more straight here. And here I want to have A12 minus 2 times A22. 3. And A13 minus 3 times A23. And I keep the second row. A21, A22, A23. Now this is A31 minus 3 times A21, A32 minus 3 times A22, and A33 minus 3 times A23. Okay. Can we find out the matrix? Sometimes it's easy, sometimes it's not easy. Because here you see, in this problem, the problem is we make the impact on 2 different rows. If you make impact on 1 row only, maybe it's easy. But then on 2 different rows, then you have to be very careful. Now, this one multiplied with this one, you should have what? We should have what? This is 1. This one should be minus 3. And this one should be 0. Yeah. Now, if you multiply this row with this one, is it A11 minus 321, right? And then this row with this column, A12 minus 322, right? This one, this column, A13 minus 3 times A23. It's okay, right? Now, how about this one?
0,
Multiply
1,
this one, you should have A21.
0, 1,
This
0,
one, A22, A23, it seems like.
0, 1, 0.
Okay, now this one. This
0,
one, multiply with this one, you should have A31 minus 3 times A21. So this is 0. What is it here?
minus 3, 1.
Can you check? This one, minus 321 plus A31. This one with this one, minus 3 A22 plus A32. Okay, correct, right? Is it okay? You know the rule, right? You know the rule. But in case, so you see, in case I'm a little bit worried because here I do 2 times of them. So in the case that it's too complicated, what should we do? We go step by step. Now you see, this one is okay, right? Now, let me do, okay, this one easy. But then I'm going to show you that I can do it slightly different so that I can split this one into the following one. Now, imagine that I do the following. Now, for this one, still this one, I show you that we can do it differently. Now, solution 2. I may call it solution 2, yeah? Now I do it slightly different, everyone. So I have this one. A11, A12, A13. A21, A22, A23. A31, A32, A33. Now, because this one I might impact on 2 different rows, I'm afraid that, okay, we do 2 different rows at the same time, too complicated. So I'm going to do it like step by step and see what happens, right? For example, here I just require that I only do with the first row. A11 minus 3, A21. A12 minus 3, A22. And A13 minus 3 times A23. And here I keep A21, A22, A23, A31, A32, A33. You understand what I mean, right? I just make impact on the first row. I subtract the first row by 3 times the second row. Then I have that one. Then what is the matrix here? This A 1 minus 3 0. And this is what 0
1 0
0. And this is
1 1.
1. Is it okay? Now, next I do the following, everyone. I start with this one. Let me see. Now I start with this one. For example, I start with this one. I have the A11 minus 3 times A21. A12 minus 3 times A22. A13 minus 3 times A23. And here I got A21, A22, A23, A31, A32, A33. Now I want this matrix become the following. Everyone. This is A11 minus 3 times A21. A12 minus 3 times A22. A13 minus 3 times A23. Now the second row I keep the same. A21, A22, A23. But here I want to do the following with this one. This is A31 minus 3 times A21. A32 minus 3 times A22. A33 minus 3 times A23. Okay? But if I do that, I multiply with what matrix here? This one multiply with this one, I should have the first term. Therefore, it should be 1. Oh, is it okay? Yeah, you can see you multiply like this, keep this one. Now, this one I multiply with this one, I should have the second one. Let's see, 0, 1, 0. Is it okay? Now, this one, multiply this one, I should have this one minus 3 times this one. So this is 0, minus 3, 1. Can you see that? Yes? Okay? So now, if I combine these two together, now I have this matrix, I rewrite this matrix. Everyone. I have 1, 0, 0. 0, 1, 0. 0 minus 3, 1. Now, the whole matrix here, I replace by this one. So I have 1 minus 3 O 1 O 1 multiply with A11, A12, A13, A21, A22, A23, A31, A32, A33. And then this one equals this one. I have the following. A11 minus 3 times A21. A12 minus 3 times A22. A13 minus 3 times A23. Keep the second row. A21, A22, A23. Now, this one I have A31 minus 3A21. A32 minus 3 times A22. A33 minus 3 times A23. Got it? Is it okay? And if you multiply these two matrices together, what is this, everyone? If you multiply the two matrices together, you should obtain this one. You can check. This one turns out to be 1 minus 3, 0, 0, 1, 0, 0 minus 3, 1. You can check very easily. Yeah, you can do it, not hard at all.
Cũng giống hay là tự viết thôi. Chết quá.
Okay, that's the key. And then you can imagine that if I do it more complicated, still I can multiply with some matrix on the left or some matrix on the right. But keep in mind, if we do something with the row, it must be multiply some matrix on the left, column a matrix on the right. Now let's go to that's A, right? I know. Yeah, F. Now F. Now let's go to F. Let's go to F. Now, delete second column. Delete second column. Of A. Delete second column of A is the following. So you have, because this is column, so I can get that I will multiply some matrix on the left. On the right, A11, A12, A13, A21, A22, A23, A31, A32, A33. And I want to multiply some matrix here, everyone. And then it's become the following. Delete the second column. So this means it should be A11, keep it, A21, A31. But then I don't have the second column. Now next, the first column, A13, A23, A33. So you see, this is a 3 by 2 matrix. This is a 3 by 3 matrix. So this matrix should be what, everyone?
3 by 2.
This must be 3. This is 3. So this must be 3 first, right?
3 by 2.
But then we have only 2 columns. So this is 2 here. Okay? Now, multiply this row with this column. And then you should have A11. Multiply this row with this column. You should have A11. So what is it, everyone?
1,
1,
0, 0.
Is it okay? Now, you multiply this row with this column. You got A11. You multiply this row with this. Okay. This row with this column. You have A21. This row with this column. You got A31. Correct? Now, the second one. 1, 2, 3. Multiply this one with this column. You got A13. So what is it?
O.
O, 1. Yeah, and then you can check this row, this column, you got A23, this row, this column, you got A33. It's okay? So this is how we delete one column. Imagine you do similar thing if we delete one row. Is it okay? Yes. Can you do it by on your own, right? Because similar line that one I do before. Yeah? Exercise 2.2, can you do it? Can you do 2.2? Yeah, so I leave last one for you to do at home because it's just the matrix multiplication line in parsimony degree. Yeah, I skip that one. Okay, right? 2.3. Can someone help me with 2.3? Yeah, go up here and work. I need someone to do question A and another student do question B. Yes? Which one? A. Do A or B? A, okay? I need someone to do B for me. You find out x and y so that a squared equal to I. Can you do it? Yes? And you too, please.
Cái này là cũng sai vấn đề.
I have now is the following. Yeah. I mean, of course, there actually is a shorter way to prove, but let's see. Now, A times A inverse times A times A inverse equal to I times I equal to I. It's okay, right? It's okay. So far so good because we use that one. This is one dimension. And then you see, you together with this one. Hang on, actually this is two dimension everyone. I can do the following. No, I can make No. Okay, I think I have better way. No, I think I have better solution here. Now, equivalent to now A, I write the following. A times A inverse. Now A times I times A inverse equal I. Is it okay? Right, because A times I is just A, and because we have from here, then we have this one. Now this I replace by what? A. Now this I replace this I by this one again. A times A times A inverse times A inverse equal I. Is it okay? Is it okay? Therefore, I have the following. Therefore, I can write A squared times A inverse times A inverse equal I. Is it okay? And therefore, it means that A inverse times A inverse is the inverse of A squared. And that's it. That's it. Yeah. And actually, A squared, we took the inverse, that will be A inverse times A inverse. But that is just one way, right? Even we have another solution, everyone, another solution. A is invertible. We know that we have a one property. A is invertible if and only if that A not equal to 0. Okay? And remember, remember, dash A not equal to 0 if and only if dash A times dash A not equal to 0. Is it okay? A number not equal to 0 is mean it's equivalent to the dash number square not equal to 0. But we have a property now, look at it. Dash of A times B equal dash A times dash B. We have that's one very special property with determinant. So that's equivalent to dash of A times A not equal to 0. But we know that our matrix is invertible if and only if its determinant not equal to 0. And then we call determinant of A square not equal to 0, therefore the solution is A square is invertible. Is it okay? So for this solution, we prove what they asked us. For this solution, we also know that A square inverse equal to A inverse times A inverse. So this one give us a little bit more, right? Not just prove what the question asked us, but also show us what is the inverse of A square. Yeah. Okay, that's the A, B, C. Now let's go to 2.9. Can you quickly explain, Kim?
The first question is to define the determinant of A, which A is a lower triangular matrix, and by applying Laplace formula and
Laplace formula for the first row, right?
for the first row, and now we have this part, and for another row, because this is lower triangle matrix, so we have another row that Hij is larger than I, and when we have the 0 here, so that's why the leftovers is only A11.
Yeah. Because the other
this
one
will
will be
be,
0 multiplied.
diagonal elements.
Yeah.
And then we continue the Laplace formula for the second row, I22.
No, for the new determinant.
Yeah, this one.
For the new determinant, and then we go with the first row as
Yeah.
well.
For the determinant,
No,
or
that is Yeah, so it means something not correct here. We use the Laplace formula again for the first row here. Therefore, this one is not 2, 1 plus 2. 1 plus, correct? Yes. 1 plus 1. Yeah.
And we also have only the leftover of the element A22. And so on, we will have like the product of I with I flow from 1 to n, with n in the side of the matrix.
Yeah.
And for the next question, if we have matrix A here is the identity matrix, and we also apply the same method at the previous one, and we also calculate that the determinant of identity matrix equal.
Actually, you can more, we call the identity matrix, you see, identity matrix is a lower triangular matrix.
Yes.
Can you see that? So you just apply the formula you just found here.
Yeah.
You don't have to do it again.
Yeah.
Yeah, of course you can do it again and so on. That's okay. Yeah.
And for the next questions, if the matrix A is invertible, we prove that determinant of invert A minus 1 equal to 1 over determinant of A.
Yeah.
And from the definition of invertible matrix, we have A multiplied with A minus 1 equal to identity matrix, and we apply the determinant both sides. We got this one, and from the previous question, we have the determinant of I equal to 1. And by applying the property of determinant, we have determinant of product matrix A and B equal to each product of determinant A and determinant of B. So that we can conclude that determinant of A minus 1 equal to 1 over determinant of A. And for the next question, if we have A is invertible, so we have this solution from C, and this only true that if we have determinant of A different than 0.
Yeah.
So that's prove up when we have from the definition of determinant that.
Yes. Actually, we can argue from here even better. You see, that A times that A equal 1, so that A cannot be 0 for sure. But because if that A equal to 0, then we don't have this identity. Okay? Well, because you don't multiply by anything zero. Then you can start here from here. Okay, good. Is it okay, everyone? Any questions? Yeah. Now let's go to (2.10). Number 8. We have a square matrix. We resolve from A by adding a multiple of a column or row. Okay, row or column of A to another column. Okay. And then we got A to 1, A to 2, blah blah. A to A. And we have so on. We have A and 1, A and 2, so on, A and N. Okay? Suppose we just have A like this. Now, B is a matrix by adding a multiple of a column. Okay, column or row are the same. A column to another column. Now, suppose I do the following. B, I do the following, everyone. B is the following matrix. I add the last column to the first column. Oh no, I multiply the last column with some number, let's say number alpha. Then here, let's see, A11 plus alpha A1N. A21 plus alpha A2N. And let's see, and so on. A(n)(1) plus alpha A(n)(n). That's the first column. Now I still have the second column here. And then the other column stay the same. Yeah. Okay, and now we prove that. Prove that then B equal that A. Actually, if you remember in your linear algebra course in Postman study, we use this property a lot. Yeah. It means that if we multiply one column or multiply one row with some number and add it to another column or add it to another row, then the new matrix has the same determinant with the previous one. And now we need to prove it. Is it easy to prove? How can we prove it? That is a section.
We rewritten by matrix multiplied with H matrix.
Sorry?
I can rewritten B is by matrix multiplied with H matrix.
Yeah, and then?
And then I will determine B.
Yeah, find determinant of B and
then determine of B is determine of matrix multiplied with determine.
Okay, I think maybe it's very technical. Can you come here and then write out the solution? I'm not sure whether it's correct or not.
So we have a knowledge check.
Yes.
So we can use the formula of the determinant, and we just select the first element of each matrix, and we deploy the formula. Then we can find it.
Can you also go to another side and write your solution? Mình nên tập thể dục cô ghé.
So can I erase the question to go back here?
Anh lấy cái ghế ra, anh ngồi ngay phía trên vậy. Actually, this is one property of determinant we use a lot in undergraduate, right? In your personal degree. But we didn't mention about the proof Here they want to clarify the property. There are different ways to prove for sure. This method, if he see this one, he have this matrix, and then he realize that this matrix he can write into the product of two matrix like this. The first one is just A, the second one is this matrix, and this matrix is all the entry on the diagonal are 1. All the entry up here are 0. Now you see this is 0 and so on. The very last one is alpha. All other entries, you imagine that all other entries here are 0. Only the first column, you have 1 here, and the last entry are alpha. Now you see, if you multiply this row with this column, then you got A11 plus alpha A1n, and this is here. Right? And then if you multiply this one with the second column, then you got A12 only, and so on. Now, if you multiply the second row here, this is right. This is A21, A22, A2n. Now, if you multiply the second row here with this column, then he got A21 plus alpha A2n, and this is here. Then we can check like this. Okay, so he write matrix B into the matrix multiplication of the two matrix, and then we apply the property up there. The determinant of a product of two matrix equal to the product of two determinants. So determinant of B equal to determinant of A of this matrix, but this matrix is just A, right? This matrix is just A, and multiply with determinant of this one. But then you see all number here are 0. All number here are 0. We only have this one. This is a lower triangular matrix. Determinant of this matrix is 1 times 1 and so on. And then this is just number 1. Number 1. And finally, this is A. This is another approach. And both are correct. Both are correct. Okay. B is the same, and B is similar. So I skip it. This means if you